Let's see how y'all did. Example 7b. The parent function is log base 1/2. So you might want to go off to the side and give yourself just a little reference so you know at least what you're starting with. Log base 1/2 or log base 0.5 are the same thing. Remember that the characteristics that they all have in common of the form log base b, they all have vertical asymptotes at x equals 0, and they all have x-intercepts of 1, 0. And then since this one is a logarithmic decay, you're just going to draw it decreasing, something like that. So there's your starting graph. So now to put this one in standard transformation form, the function's name is a, the independent variable is x. The one in the front is what letter in the standard transformation form, A, B, C, D, or D? Yeah, the +1 is the term that's being added, so it's not the a value, it's the d value. So he goes to the back, and he's a positive one. The 3 in front of the log is your a value, and bless you. Now on the inside, remember, that's where kind of most of the fun resides. You got to do two things. You got to first put the x term first, so I'll do it like that, and then you have to factor out the coefficient of x, whatever it is, if it's something other than 1. Otherwise, your shift is incorrect. So we have to factor out the negative on the inside, and now we get x minus 4. Okay, so the 3, if we want to go ahead and start getting ready to sketch it, the 3, of course, is going to be a vertical what? Stretch by a factor of 3. We don't have to show that on the graph. The negative in front of the x is a reflection across the y-axis. Yeah, your x's are trading place. That one's a pretty significant one because that's going to now make the graph live to the left of the vertical asymptote, which changes the domain. And then the -4 moves it which direction? To the right 4. And that's significant because that's your vertical asymptote. It was at 0, now here it's at 4. So I'll draw the dotted line. And then the +1 moves it up 1, which is not really something we need to show. But it does now become a growth function. Since we flipped it across the y-axis, it's going to look something like that. And again, you have to be careful because there is the opportunity, especially in this case since we're shifting it up 1, it may cross the y-axis in positive land or negative land. So on your own, without being solicited to do so, you might want to find the y-intercept. And it's easier to plug it back into the original, not the standard transformation form. That one's good simply for sketching it. So if you plug in a 0, you're going to get 1 plus 3 log base 0.5 of 4. Now, is log base 0.5 of 4 a positive number or a negative number? It's positive? Let's go off to the side. That's like a problem in and of itself. I'm going to call that log base 1/2 of 4. And this is kind of like what we did in the warm-up. I can write 4 as a power of 2, right? That's log base 1/2 of 2 squared. And then to get it to flip, I do what with the exponent? To turn a 2 into a 1/2, I have to change the sign on the exponent. So what is log base 1/2 of 4? -2. Oh, okay, cool. So see how we have a fun problem inside of another fun problem. So what's -2 then times 3? -6 plus 1 is negative. Okay, so that is that's a negative number. We can actually evaluate it. What do we say it was? -5. Let's do that first. Let's say it equals -5, which of course is less than 0. So the way I have it drawn right here, as it turns out, is good. I can leave it like that. There was the possibility, though, since we shifted it up 1, that it could have been a positive number. All right, so there it is. That's the graph. Kind of anticlimactic at this point. But let's go ahead and kind of talk about some of the features. The domain of the function is probably the most interesting question. It's the set of all x's such that x is strictly to the left of 4. Now, before we go on and talk about something else, let's verify that algebraically. If you had shifted it or reflected it across the wrong axis, you might have the wrong domain. I told you yesterday how to find the domain of a log function. What is this thing called we're taking the log of? The argument, right? And so to find the domain, your argument has to be strictly positive. So you're going to take it, 4 minus x for us, say it's strictly greater than 0. And now you solve that inequality. That one's linear. Can we solve it algebraically? Yep, as long as we remember that little correction. When you multiply or divide by a negative number, you flip the inequality. So to solve for x here, we either divide or multiply by a negative 1, so we will flip the inequality, and we get 4. And this one says x is... Oh, yeah, I flipped it prematurely. I did a double flip, yeah. So notice that they don't match up, so something is wrong. You either made a mistake in your graph, or you made a mistake in your algebra. And I can see right here, yeah, y'all caught it too. Mine in this case was in the algebra. The algebra is supposed to be the verification, not the one you mess up on. I just flipped it too early. I got excited. It's Friday, it's December, what can I say? So yeah, x is less than 4. And now they do match up. So now that means that you more than likely have the right graph. What's the range of this function? All real numbers, all real numbers. And then 2 limit questions that I might ask, the interesting ones. The limit as x goes to negative infinity of a of x is what? As you go out to the left, right, the graph goes down, down, down forever. Yeah, negative infinity. Let me go ahead and throw this one in here. We mentioned this yesterday. I probably wouldn't ask this on a test or quiz, but it's a fair question. What is the limit as x goes to positive infinity? D and E, right. Now remember, when you say on the first one that the limit is negative infinity, you're saying first that the limit doesn't exist, but it's because the y values are there, they're just decreasing without bound. In this case, you're saying that the limit doesn't exist because there's no y values at all to mention. All right, then the last one that I kind of like is the limit as x goes to 4 from the left-hand side. 4 is the vertical asymptote. As you approach it from the left at 4, the y values are going to infinity. Yeah. So any one of those questions could show up on your test next Friday. I could just give you this graph, and I can ask you what is the limit as x goes to negative infinity, or what is the limit as x goes to 4 from the left. So graphing it is just one of the ways that you could do that. Okay, while we're here, just to reinforce it, there's a vertical asymptote at what? Yeah, if you just say 4, would you get credit? No, it's an equation, and it's an x, right? So a vertical line, remember, is of the form x equals, and the horizontal line is of the form y equals. All right, sweet. Any other comments or questions about 7b? Ho, ho, ho. All right, example 8. Find the domain of the following. Again, you can make great multiple choice questions and great stocking stuffers for your loved ones. F of x is 3 minus 4 natural log of x squared minus 9. For the domain of a log function, remember, we take this thing that we're taking the log of, called the what you meant? Argument, sweet. And we say that it's what? Greater than or equal to 0, greater than 0, less than 27? Strictly greater than 0. Yep. When we had radicands, remember, on even roots, we said that it was greater than or equal to 0. We could take square roots, 4th roots of 0. But for logs, we can't take log of 0. There's a vertical asymptote there. Now we have an inequality to solve. Can we solve this one algebraically? No, why not? It's quadratic, and quadratic is not linear. So the way we solve these, remember, is not giraphically, but graphically. Good. I don't know how you would do something giraphically. With a long neck, maybe? Big graph, right. Tall graph. All right, so x squared minus 9 shouldn't take you any time at all to sketch. It has a y-intercept of negative 9. It's a parabola that opens up, looks like that. Remember, for the quadratics, it's either going to be everything between the x-intercepts or everything outside the x-intercepts. And we've had a lot of practice with these. We want to know where the graph is positive. So it's everything outside the x-intercepts. So we need to find the x-intercepts. And again, for something like this, at this level, you should be able to look at x squared minus 9 and know the x-intercepts are at 3 and negative 3. Yeah. But if you're not sure, you could factor it, x minus 3, x plus 3. It's a difference of squares. Or you could come off to the side and set it equal to 0 and then solve by extracting both square roots. However you want to do it. There's negative 3, there's 3. And so now it's everything, because it's a strict inequality, everything to the left of negative 3 and everything to the right of positive 3. That's going to guarantee positive values. So now we just write it in fancy notation. D sub f colon is the set of all x such that x is less than negative 3 or x is greater than 3. And remember, this is the disjoint set. These two intervals that we have do not overlap, so they're separate intervals, and so you write it as two separate inequalities. You don't do it like this. All right, if you look at that, that still has the alligator eating the correct thing, right? The arrows are pointing to the right thing, but this is not correct. Okay? It's like bad grammar. First of all, we want to go from least to greatest, and this is the compound inequality which we reserve for the and case, if it were between the two. Okay? All right, this one here. G of x is 2 plus log of 2 minus the square root of x. Cool. Finding the domain. There's the argument. We say that it's strictly greater than 0. Can we solve this one algebraically? Is this linear? If it's x to the 1/2, is it linear? No, linear is always x to the first. That's not a line. That's a radical function. So we have to solve it how? Graphically. Cool. So this is a way for me to kind of throw in a graphing by transformation of a parent function to you, right? So if I just set the argument equal to y, I want to graph y equals 2 minus the square root of x. So like we've already done, graphing parent functions with logs, we'll put this into standard transformation form. And remember, if you want over here to the side, for reference, your parent function is the radical function. So don't forget all the parent functions you've already been working with. What is that going to do to the graph of our parent function? The negative in front is going to reflect it across the axis, right? The axis. What axis? X-axis, right. Confident at the top of your voice. It's going to reflect it across the x-axis. That makes it open downward like that. And then the +2 moves it left, right, up, or down 2? Up 2. Okay, sweet. So here's 2. There's the genesis point. And then it's going to open down and to the left. Or down to the right. Y'all's left. Nope. Y'all's right. Okay, whatever. Now we need to answer the question. Go back to the original inequality. We want to know where that graph is greater than 0. That means we want to know where it's above the x-axis. That's in this tiny little interval right there. So not surprisingly, it comes down to finding the x-intercept. How do we find the x-intercept of this function? How do you find the x-intercept of any function? Set y equal to 0. Good. So I'm going to say 2 minus the square root of x, set it equal to 0. And now because this is an equation and not an inequality, you can solve it algebraically if you don't know what the answer is. I'm going to bring the square root of x to the right side. So now I get 2 equals the square root of x. And then to unsquare root something, I do the inverse, which is square both sides. And you end up with x equals 2 squared, which is 4. So now that we know the x-intercept, and we know what the graph looks like, we can write the domain. The domain of this function g is the set of all x's such that. Now, is this a disjoint interval or a connected interval? It's connected interval, right? It's everything between x equals 0 and x equals 4. All right, so if you want to do the inequality now, you could put x in the middle, and these are less than or equal to's. You put the number on the right, the number on the left, on the left. And now we just want to make sure we have the inequalities correct. Can I include 0 or not? At x equals 0, is that graph positive? It is. So I could put a less than or equal sign here to include the 0. Can I include the 4? 4 is the x-intercept. Is 0 a positive number? No, it's not. So there's your interval right there. If you want to write it like this, x is beefy bracket at the 0 and a wimpy parenthesis on the 4. That function is positive at 0 and everything between 0 and 4, but not at 4. So kind of a cool one, right? I like that. So as you're preparing for next Friday's test, you might want to review, if you don't know it, all your parent functions. Go back to that section. We gave them all to you in that little table, catalog of parent functions. Because I could throw them in there now as the argument and have you graph them. All right, comments or questions on that one? All right, well then example 9. Here's a chance for you to shine. It says find the domain, part A, of h of x. If h of x is 3 log base 4 of log base 5 of x. All right, I'll start you off on this one. We have kind of like a compound log expression or equation here. Because we have 2 logs, we have 2 arguments, don't we? We have the first argument, if you just look at log base 5 of x, the first argument is x. So I know that x has to be greater than 0. But log base 5 of x itself is the argument for the log base 4. So we also know then that log base 5 of x has to be greater than 0. Now, if you want, you could just focus on the inside, log base 5 of x, and say it's greater than 0. Because if it works for that one, it's going to work for x is equal to 0. So here's what you want to do. You got to solve this inequality, and whatever solution you get from that, it should be greater than 0. You'll check that. And so remember, we can only solve inequalities algebraically if they're linear. Is a log function linear if it has an L in it? No, it's log. So here's what you have to do, and I'm going to let you do this. You have to graph y equals log base 5 of x, and then tell me where is that graph strictly greater than 0. Go for it. You're solving the domain or finding the domain by graphing the argument. While you're doing that, I'll do it quietly off to the side here. All right, let's see what you did. So if we're graphing log base 5 of x, that is your straightforward parent function log base 5 of x, which is logarithmic growth because the base is 5. So it looks almost exactly like the natural log of x. Would it be steeper or less steep than the natural log of x? Less steep. Good. Because remember, the natural log's base is e, which is like 2.7. This is base 5. And as we saw yesterday, the smaller the base, the steeper the graph. And because e is smaller, it's going to be steeper for e than it is for base 5. All right, but anyway, we want to know now where this graph is strictly positive. That is above the x-axis. And you could tell then that because the x-intercept is 1, 0, you knew that, it's going to be positive y values everywhere to the right of 1. Now, it has to satisfy both arguments. So, if this one says that x has to be greater than 1, does that also satisfy the fact that x has to be greater than 0? Yeah, everything bigger than 1 is bigger than 0. So when in doubt, if you have multiple arguments for your domain in one function, you got to take the one that works for both, or all 3, or all 4, whatever the case may be. Not everything greater than 0 is bigger than 1, but everything bigger than 1 is bigger than 0. So there's your domain. Everything bigger than 1. So really all we did is we just did what we did on the previous ones. We just graphed the argument, found where it was positive. All right, so now part B, and this is, there's a couple of questions on the worksheet that have you finding the inverse of a log function. This one is going to be fun. How do we, in general, find inverse equations? Yeah, very good. To find inverses, you're going to switch or interchange, whatever you want to call it. You're going to switch x and y, and then you're going to resolve for y. So h to the negative first is h inverse. So let's go ahead and do that. H of x, remember, is just a fancy name for the y value. So as you're writing it down, you might want to write it down as y equals log base 4 of log base 5 of x. And there's a 3 there. I forgot all the other stuff that went with it. The 3 and the plus 8. So let me remodel here. The 3 goes here, and the plus 8 at the back. So that's just rewriting down the original function, but replacing h with y. All right, so the money step in green here is the switching the x and y. So now we get x equals 3 log base 4 of log base 5 of y. And now all we got to do, algebraically, is peel back the layers so we can get at the y. All right, so what's the first thing you would do to start solving for y? You have to first isolate the term that has the variable in it. So that's the first term. So we need to get rid of the plus 8, right? It's just like in algebra. If this were x equals 3y plus 8, you would subtract 8 and then divide by 3. That's what we're going to do here. We're going to subtract 8 and then divide by 3. That's going to give you x minus 8 divided by 3. So I did two things in one there. So hopefully you can do that as well. But if you can, just do them one step at a time. Subtract 8, then divide by 3. Now we have our variable factor isolated, and we have to start peeling back the layers from the outside in. So right here, I have log base 4. How do you undo logging base 4? Exponentiate base 4. Good. And I said that I was okay with you kind of cutting a corner here and just using that line and make them exponents by putting the 4 on the bottom left instead of having to write a whole new line. So on the left, we're left with 4. You could leave it as x minus 8 over 3, or you could write it like this. Dividing by 3 is the same as multiplying by a third. That kind of makes it look a little nicer. I think I'll do that. But on the right-hand side, we have 4 to the log base 4 of blob. And so what are we left with? The blob, right? We're just left with log base 5 of y. So that got rid of one of the log layers, and you can see that we're making progress. Now I have to get at the y by unlogging it base 5. So I'll do a very similar thing. I will now exponentiate both sides base 5. And it looks like I'm going to shrink this down here to give more room. Okay. So now on the left side, we got something that looks like it's kind of climbing a ladder here. 5 to the 4th to the 1/3 x minus 8 power. And that would equal, what's 5 to the log base 5 of y? Should be y. We succeeded. We solved for y. So now that you've succeeded and solved for y, you want to give y a new name, because that's generic. We're going to call it h inverse. And so we'll flip the side around as well. So we got h inverse then of x equaling 5 to the 4th to the 1/3 x minus 8 power. Is there any way we can kind of clean that up? Not really. So you just have this 3-tiered thing. Because we had 2 logs, we're going to have like 2 exponents. And not surprisingly, one of them is base 5 and the other one's base 4. So inch by inch, it's a cinch, right? Piece by piece. Just like you learned in Algebra 1, you're peeling back layers as you see them to get to the inside. You just have this new tool now called exponentiation, which undoes logs. All right, so example 10 actually is a little bit easier than example 9. So I gave you the hard one first, and I'm giving you the easy one second. So you could think of example 10 as kind of a cool-down problem, right? After you work out, you have a cool-down problem. Go ahead and do this one on your own. I'll give you about 3 minutes. Doing the same things we did above, but just with an easier function. That's 3 minutes. Let's see how far you got and how you did it. All right, so the first one, part A, find the domain of a log function. So reflexively now you should look for the argument. That's the thing you're taking the log of. In case this 2x minus 4, and you say that it's strictly greater than 0. So that's what you do each and every time. 2x minus 4 in this case is linear. Boring. We get to do it algebraically instead of graphing. You could solve it graphically if you still wanted to. But this is linear, so I added 4 to both sides, divided by 2, and I got x is greater than 2. So we're going to go with it. I don't think I made a mistake on that one. So the domain is everything greater than 2, so you can write it in set notation, or interval notation is the one on the bottom. X epsilon, remember that means x is in the interval from 2 to infinity. Bonus question. What is the range of that function? All real numbers, yeah. That's kind of a boring question for a log function, because it's the same for every log function. The range of any log function or transformation of it is all real numbers, just like the domain of exponential was all real numbers. Okay, so now finding the inverse. I replaced h of x, or f, sorry, with y, and then the money step on the next line was to interchange the x and y. So I stopped right there. So now we got to peel back the layers as we see them and get to the y. What would be the first thing we would do? Subtract the 3. Good. And I'll show this one in 2 steps. The line before I did it in 1 step. All right, so if you subtract the 3, now you have an x minus 3 on that side. Now that you have the term isolated with the variable, now you got to get the factor isolated. And so right now on the right, we're multiplying by 2, so the inverse of that is dividing by 2. So you end up with x minus 3 over 2. equals log base 1/2 of 2y minus 4. Looking good. We're getting there. And now the new skill. We have log base 1/2. We got to unlog it by exponentiating it. Whenever you have x or you're exponentiating and your base is a fraction, you should put your fraction in parentheses so that you know then that the entire rational number is raised to that power, not just the numerator. All right, so we're left with on the left side a 1/2, and if you want, you could write that as 1/2 times x minus 3 instead of x minus 3 over 2. And the right side, good things will happen. 1/2 raised to the log base 1/2 of something is just that something. So you get 2y minus 4. All right, now you got to solve for y, so what do we do again? We got two terms now. We got to get the term with the variable isolated, so the inverse of subtracting 4 is adding 4. So I'll make a new column over here. We'll have 1/2 to the 1/2 x minus 3rd power plus 4, and that should equal 2y. And then the last step, got to undo multiplying by 2 by dividing everything by 2. But instead of dividing by 2, that's equivalent to multiplying by 1/2. Yeah. If you just divide by 2, you'll have all of that over 2, and that's just kind of bulky. So what I think I'll do is multiply both sides by 1/2, and we get 1/2 times the entire quantity, 1/2 to the 1/2 x minus 3 plus 4. So the whole left side times the 1/2. Now, since we solve for y, we'll give it a better name than just y. Since it's the inverse of f, we'll call it f inverse. So f inverse of x. And what I think I'll do now is distribute the 1/2 all the way through. So if you distribute the 1/2, you get a 1/2 times a 1/2 to the 1/2 x minus 3rd power plus a 1/2 of 4 is 2. Now you can leave it like that, or you could actually do one more thing. Because the a value is a 1/2 and the base is 1/2, so the same base, you're multiplying them, you can actually add 1 to the exponent if you wanted to. But if you add 1 to the exponent, you're going to have to be careful how you do it. Because the exponent right now is factored. So if you do add 1 to the exponent, it'll be 1/2. I would probably distribute the 1/2 through. 1/2 x minus 3/2, and then you can add 1 to it. So this is like for multiple choice purposes. I would probably add those together. So distributing the 1/2 and adding the 1, I think we'll have our final answer here. We get 1/2 to the 1/2 x, and then negative 3/2 plus 1 is what? Negative 1/2, and then we have the plus 2 on the ground floor. And what the heck, I'll do one more line. We'll put it back in the standard transformation form. Now I could factor out the 1/2 in the exponent, and I'm left with x minus 1. And then the plus 2 is on the ground floor. So you got to be very, very diligent when you're writing these exponents. They should be written slightly smaller than the other numbers, and of course they should be elevated so that you can actually see the layers. But there's a nice cleaned up version of f inverse. And not surprisingly, its base is 1/2. We started with a log that was base 1/2, and the inverse ended up being an exponential with a 1/2. All right, now there's two follow-up questions here. What is the domain of f inverse? Do we need to graph that to answer it? No. What's the domain of any exponential function? The range of the log, which is all real numbers. Yeah. Remember, the thing about domains or inverses is their domains and ranges flip. So the domain of f is the range of f inverse, and the range of f is the domain of f inverse. So now it's asking us for the range of f. We've already done that. We asked that as a bonus question. So let me modify this. What is the range of f inverse? We'll change it around. The range of f inverse. Do you need to graph this exponential function to find it? No. the range of f inverse should equal, let's write that down, should equal the domain of f. And we've already found that. What was the domain of f? Everything greater than 2. So all we have to do is write it as y values instead of x values. The range of f inverse is the set of all y such that y is greater than 2. And that should be the same thing you would get if you graph it. So very quickly here, looking at what the graph of f inverse would be, it's an exponential decay function. The plus 2 is the horizontal asymptote because it moves it up from 0. And because it's 1/2, it's exponential decay. So if you were to graph it, you could actually see then that the y values are all above 2. But you wouldn't need to. As long as you knew that your domain work for f was correct, you can call that the range of f inverse. So we already talked about that back when we had those rational functions. They made it on the test. All right, there you go. There's your introduction to logs. That completes 4.3, right? 4.3. In the next section, we start learning a lot more properties with logs. So you got to make sure that you understand logs pretty well. So you get a chance to practice on your worksheet. Worksheet is not due tomorrow because we don't want to meet on a Saturday just to turn in homework. So we'll meet back here on Monday. Worksheet is due. Will we quiz on Monday? No. I said no. Yeah, we won't quiz. Yes, sir. This makes a good free response question, but your free response question is going to be logistic. So if I did ask this as a multiple choice, I might say something like, if f of x is equal to this, here's what the question might be. If f of x is equal to that, what would the range of f inverse be? That makes a good question. And you'd realize, oh, the range of f inverse is just the domain of this function, and then you set your argument equal to 0 and get x is greater than 2. So that makes a slightly better question than just asking what's the domain of f, right? It's the same work. You just have to understand what you need to do, and that it is, in fact, the same.